Okay, so let's talk about Laplacian operators. There is a great history about Laplacian operators. And for example, in 1D, transverse wave equation, utt minus c squared uxx is equal to 0. Because I've studied aerospace engineering, fluid mechanics, all of them, wave equations, thermoacoustics, Laplace, all of them, I've touched all of them. So it is really in physics, but we can extend it, and people have generalized it and used the discrete version of that for machine learning, because it naturally appears when you solve an optimization problem. As you have seen in my previous lectures, it naturally appears. But so let's talk about the physical perspective, why it appears in physics and how it is related to this continuous case. So first, the continuous case. The continuous case is just all of these PDEs. And for example, the Laplace operator is just minus. Some physicists say this is plus. Some people say it is minus. So f, your function, is infinitely continuous, differentiable, and you have a constraint that at boundary condition it's 0. So your eigenfunctions are phi kx is equal to 2L pkx. These happens in thermoacoustics, in combustion instabilities. I've seen it in several places in physics. pkl2. So this L, you can hear the length of an interval because L is interval, and because it's a wave, and because in 1D transverse wave you can, there is something called, can you hear the shape of a drum, and those historical things. So let's talk about wave equations in 2D. So in 2D, your wave equations is becoming more interesting because it is equal to minus Laplacian, and the Laplacian is just an operator. What is an operator in infinite dimensional analysis? You give it a function which is infinite dimensional, you get another function which is infinite dimensional. So it's minus xi squared. So in this region, this is the boundary of that, and this is the domain which is inside R2. So this is Laplace. You can write it as a divergence of gradient. In weak convergence and those things in elliptic theory, all of the you need to understand weak convergence as well. It's a great, interesting, important topic, especially if you want to understand shock wave. How do you model mathematically something which is really discontinuous? It's very interesting, but you can represent your Laplace like this as well. But very important things for both machine learning guys and physicists is Dirichlet energy. Dirichlet energy, when you minimize energy of any function, your U is infinite dimensional, so it's a function, and it's a function. minimize this subject to u at the boundary of your domain is prescribed, you know it, is equal to minimize 1 over 2. It's like sum of all gradients, norm of gradients in a specific area, specific domain. It's like this minimization is like finding the smoothest function that you can find. And it turns out that this nice smooth function that you are looking for is just the Laplace equation. And some people say, in functional analysis, it's a huge topic. They call it harmonic theory, harmonic analysis theory. But you can say it's just a Laplace equation. So the idea now, signal processing guys should be interested in that. Also, those filtering guys in image processing. The reason that they are excited about these things is that when you have non-smooth function, what does it mean? It means that it has many variations, goes up and down, many higgles, many local maximum, local minimum. So this is non-smooth. But it is smooth. If it is constant, if it goes like this only, no variation, so Laplace plays an important role. Also, it is like it holds the mean value property. So the mean value property is interesting because f of x is like the average of all values locally. So f of x is 1 over pr squared integral of a ball at point x, f of y, d of a. This is really important. In filter theory, in image processing, this is an important idea to understand how nonlinear filters in image processing, the theory is developed by these ideas. And also your eyes behave like that, Your eyes, even when you just look at one point, it is moving because it sees the Laplacian, it sees the change of change. And that's interesting. Even if you just focus at one point, still your eyes are moving because it wants to understand the relationship with its neighbors. Otherwise, it is meaningful. Otherwise, you cannot even see anything. So Laplace operator is a infinite dimensional analog of positive definite matrix. It's very interesting because in Stokes' theorem, you see that a positive, it is the inner product of f and Laplacian of f. This inner product is greater than equal to 0. And it's like saying that you can write as this, and this is equal to gradient of f squared, and this is greater than 0. Of course, it is energy. And the inner product in functional spaces can be written as f of x, g of x, d a of x. Of course, you can define it very differently, for example, but there is a second part, is that it is self-adjoint. It means that in quantum physics, everything about self-adjointness. So this is an operator. Our operator is the Laplacian. So the inner product of f and Laplacian of g is equal to Laplacian of f and G. So it's self-adjoint. And now let's talk about Laplace operator on graph. You have some nodes like V and W. It can be directed. So what is your energy? Your energy you can define as norm of dF, because d is now operator, and it is a differencing operator. An operator working on f becomes a function, and here it is the discrete, so you can extend it for discrete spaces as well. So when you square this norm, it is like for any node V and W, f of V minus f of W squared. So let's look at this more carefully. What does it mean? Because something is squared, okay? So you can write it as df. And if you group these together, it is just L Laplacian. So that's why this one is F transpose LF. Don't forget that our differencing operator here, this differencing operator, this is differencing operator of edge and vertex is equal to -1 and 1, and otherwise it's 0. So Laplacian VW is like my previous lectures, is A minus diagonal. So D is a degree matrix. And now you understand why I talked about locality discriminant analysis. So all of these things are now obvious for you. And A is adjacency matrix. And A minus D is 1. If V is W, it's minus degree of V. And otherwise, it's 0. And now let's talk about some more preliminary things about discrete Laplacian operator on graph from a different perspective, slightly different perspective. We have some nodes such as V1, V4, V2, V3, some nodes. And also we have some edges, E4, E1, for example, E2, for example, E5, and E3. So you have a graph of some vertices and edges. And now let's see what is gradient. What do you mean when you see gradient in a graph? Gradient is cardinality of E, cardinality of V, edges and vertices, and gradient transpose, is like transpose of that. So it's like E. So gradient is a matrix. It means that if you have even edges, you have 5 edges in this example, and you have 4 vertices. Okay. For example, for this graph, it is -1, 1, 0, 0, -1, 0, 1, 0, minus 1, 0, 0, 1, 0, minus 1, plus 1, 0, 1, minus 1, 0, 0. So if you multiply gradient by a vector, such as, for example, v1, v2, v3, v4, what does it mean? For example, it becomes minus v1 plus v2 minus v1 plus v3 minus v1 plus v4 minus v2 plus v3 minus v3 plus v4. And so because gradient transpose is now 4 by 5, if you multiply it by gradient, which is 5 and 4, it is well defined and it becomes 4 by 4. So you see how Laplacian operator, you can see it from a different perspective. Now let's talk about manifold regularization. So we want to, your regularized learning is like arg mean of, you have L samples, V, f of xi, your estimator, and yi. Of course, this loss function could be anything, not just L2. So plus gamma norma of f2. But this is your regularizer, which is defined as integral of gradient of f of x squared, and this is f transpose LF. So you want to care about smoothness on data manifold. So by adding this one, you want to say that you care about smoothness on data manifold. What does it mean? For example, at some points, okay, you have fixed your knowledge. For example, you say, okay, that function can go anywhere, but at these points should cross these points. Okay, so this should be this data on our manifold should cross that. So because we are in function spaces like Sobolev space, Hardy space, all of these spaces in functional analysis and also in harmonic analysis, all of them are infinite dimensional objects. It means that, for example, if this is a function, this can be another function, but it crosses this. This can be another function, but it should cross this point. And this should be another, but it should cross this point. So you are regularizing in the space of functions. And this is the intuition behind all of functional analysis, I can say, even Banach spaces and Hilbert spaces. If you understand this, you can understand the topology of functional spaces. How topology in geometry, for example, quantum physicists are just interested in the geometry of that supermanifold. Because each point of manifold is now a manifold. It's a supermanifold. So because I was attending supermanifold theory in Manchester University. I noticed that why quantum physicist is related to those geometry of manifolds courses. And now here, by regularization,